Okay, good afternoon guys. Good afternoon all of you. Good afternoon guys, good afternoon all of you. Okay, so let us just start the session. So in the previous session and the one before that we finished shell representation, and before that we had a look at electrochemical series and its application. We also see how electrochemical series is made, and we also saw the significance of positive and negative reduction potentials. So on the basis of that particular thing, what I told you in one of the lecture, that if there is a cell which is constructed between zinc and copper system, we can easily tell by looking at electrochemical series that zinc will be the species which is getting oxidized, whereas copper is the species, copper 2 positive is the species which is going to be reduced during the course of this cell, right? So this was the brief introduction that we already had about our cell working, and we also know that during this cell working we require a salt bridge, right? So everything which we studied so far was at standard state. We always used electrolytic solution of concentration 1 molar, whether it is ZnSO4 or whether it is CuSO4. We took 1 molar solution of each electrolyte, and we also fixed the temperature at which we studied this whole thing to be 25 degree Celsius. So now voltmeter will give me a reading which will show the difference in potential between Zn system and Cu system. So this voltmeter generally gives a reading of 1.10 watts. How we can justify this reading at standard state? We generally say that reduction potential for zinc system is negative of 0.76 watt, whereas reduction potential of Cu to positive to Cu is basically 0.34 watt. And we know by far that electrons travel from more negative reduction potential to less negative, or generally we say more positive reduction potential. So initially my electron was at 0.76 potential and finally it traveled to 0.34 potential. So what is the difference in potential between these 2 points? That we generally calculate by a formula which is basically known as E node right minus E node left, and this just tell us about standard cell potential. We generally use this formula. Right? What we say that to calculate standard cell potential, we must know the final potential and the initial potential. And when I subtract the initial potential from the final potential, I will have E node cell. That is what we generally do. In doing so, we always take reductions potential of right side cell. We always take this one as reduction potential, and this also as a reduction potential. So if I put these two values in this particular equation, I will have E node cell to be equal to 0.34 minus 0.76, and this resultant will give me a value of 1.10 watt. That is normal, right? But what I am about to tell you right now is that this particular formula is not a correct formula. It is not a correct formula. Basically, it is a reduced formula that we actually should use. Thank you, Chemistry in Telugu. Thank you very much. Do consider subscribing the channel if you are new over here, if you guys are new, and please keep sharing the video with your friends. And if you like the content on the channel, please give a thumbs up to this video as well as rest of the videos. Whichever video you see on our channel, you can give them a like. Please do consider subscribing if you are new to the channel, and if you already are watching our video but haven't subscribed yet, please do consider subscribing our channel, as well as keep sharing this video with your friends. This might help somebody who is having trouble in understanding Hindi but can efficiently learn in English. So this will be very helpful for them. Now have a look at it. What I am saying is that this is not a correct formula. This is not a correct formula. It is not a correct formula. Why is it that I am saying that this formula is not correct? This formula we are learning right from our childhood, right from our class 11, 12, that E node cell is find out by E node right minus E node left, when E node are generally reduction potentials. But this one is not, this formula is not correct. Why is it so? That is what we will discuss today. And then we will discuss what if we change these concentrations, what if we change this pressure, this temperature, what if there is a gas and we change its pressure from 1 atmosphere to some other values, what will happen to the potential of the cell. That is what we are about to start today, right? So have a look at this one. You must have read in chemistry that there are two type of property. One property is known as intensive property, whereas another one is known as extensive property. The intensive property is that property which is not number dependent. What is a number dependent property? Such as length. If we have one atom, we join another atom to it, we join one more atom to it, what we will say that length of the system will keep on increasing. So we basically can say that if we have 10 atoms, we add up their diameters and we will find the length of a particular system if all are arranged in a single row. So that generally means that the length, which is a property, which is a physical property, is basically dependent on the number of atoms within a continuous series that they are attached, right? So such property which are number dependent are generally known as extensive properties. What is an intensive property? An intensive property is basically a property that does not depend on the number, that simply depend on the nature of the system. For example, if I say that zinc, whenever it goes to Zn2 positive, it will always have a potential, it will always generate a potential of 0.76 watt, reduction potential of negative of 0.76 watt. No matter one zinc ion have transferred into Zn2 positive or one zinc ion have transformed into Zn solid, no matter 100 of them have transformed. So this is basically means that this property is not dependent on number. It is simply a nature dependent property. And when I talk about E node in particular, now this node defines standard state. We know clearly this node defines standard state, right? And whatever we write beneath this E is generally describing as the process. For example, if I have written Zn2 positive Zn, this means this is a reduction potential. This means this is a reduction potential. And if I write beneath Zn2 positive, this basically means that 0 to plus 2 oxidation change is taking place and it is a standard state that is denoted by node, and this generally means it is a oxidation potential. You talk about reduction potential or oxidation potential, their magnitude are always equal. I have already clarified it in previous lecture. If somebody doesn't know about it, they can go and watch the previous videos. The only difference in them is of sign. If this one is positive, this is going to be negative, and if this is negative, this is going to be positive. What another thing this standard state implies, this standard state put a condition. This standard state put a condition that I have fixed the concentration. Concentration of electrolytes are fixed. Another thing which this standard state implies, this is constant. I have fixed it to 1 molar, right? Another thing this standard state implies is that I have fixed pressure also. Pressure of all the gases are fixed to be nearly about 1 atmosphere, or you can say 1 bar. 1 atmosphere or 1 bar, you can easily say that. Now do remember this. If I have fixed these values, that means I have made this property to be free of concentration. Does EMF depend on concentration? You will say yes, it does depend on concentration. But while defining a standard state, what I have done is that I have fixed this concentration, I have made it constant. So basically potential is a function of concentration. Definitely it is a function of concentration. How many ions you have to reduce, that will define the overall potential. Yes, it will define the overall potential. But in standard state, we have fixed this concentration. And if we have fixed the concentration, we say that in standard state, it is independent of the concentration, because we made it constant. We put it constant. For example, we generally say that dZ is equal to SdP plus VdP, SdT plus VdP. And in one case, if I say volume is constant or pressure is constant, then I will generally mean that I have made this DG system independent of the pressure. This was a function of temperature and pressure, but pressure I took constant and I made it a function of temperature only. In same manner, potential does depend on concentration, but in standard state we have made it constant. So what we have done is that now at standard state we have made this potential independent of concentration. Independent of concentration. And if anything is independent of concentration, that generally means it is intensive property. It is intensive property. One more thing for intensive property is that we cannot add or subtract these properties. These cannot be added, cannot be subtracted. These properties cannot be added. They cannot be added. We should not add them or subtract them What does it imply? It just basically implies that my formula of E node cell is equal to E node right minus E node left is basically not correct, because these all potential are at standard state, and at standard state the concentration is constant, so it is independent of concentration. And if some property is independent of number of atom, that is concentration of a particular electrolyte, that means it is an intensive property, and intensive property should not be added or subtracted. They should not be added or subtracted at all. Now if we cannot add or subtract them, that generally means that this formula is wrong. But actually it is a reduced form of a formula. How it is a reduced form? We will have a look at it. Look here carefully and you will find a very good, interesting logic behind this system. What does I mean when I say that this formula is incorrect? Have a look at this one over here. If we change the concentration, or pressure or temperature, that generally means EMF of the cell will change. EMF of cell will change, will definitely change. More number of ions in the system, more will be the potential required or number of electron required to bring out the reduction or oxidation. So now this is experimental fact. If we change the concentration from 1 molar to 0.1 or from 1 molar to 2 molar, then there will be a change in EMF of the cell. Overall EMF of cell will change from 1.1 to some other value, any value. How it will change? That was explained by Nernst. It was explained by Nernst. Nernst did explain this phenomena. Another important key aspect to note down over here is, whenever concentration is not kept constant and equal to 1 molar, that means now EMF is definitely a function of concentration. By changing concentration, EMF will change, and if it is a function of concentration, this new EMF is generally stated to be E, not E node. This is represented by E, not by E node. And this E is also known as non-standard cell potential. Non-standard cell potential. Now this non-standard cell potential is a function of concentration. And pressure definitely. And if some physical property is a function of concentration and pressure as well, then we will simply say that it is an extensive property. And extensive property can be added or subtracted. It can be added or subtracted. Now in free state, when we have to find out the non-mechanical work, what we did was that we put delta G equal to difference in potential between the electrodes, and we multiplied it by the amount of charge carried during single cycle. Means what I said, that delta Z node is equal to negative of NF E node for a spontaneous process. Similarly, this non-standard cell potential is a function of concentration and pressure, same as my delta G for a reaction, not G node, I am talking about delta G. Free energy change, not standard free energy change. This free energy change of a reaction is also a function of concentration and temperature and pressure. So this free energy change will similarly be equal to negative of NFE cell. Just like we had delta G node equal to negative of NF E node cell. So Nernst utilized this fact and said that in thermodynamics we have studied, in thermodynamics we studied that for a reaction delta G is equal to delta G node plus RT ln QC. RT ln QC, where QC is your reaction quotient. This is known as reaction quotient. What is a reaction quotient? What is a reaction quotient and how it is different from our equilibrium constant? Let us have a look at that also. So if this is the relation valid from thermodynamics, Nernst utilized this equation. Now Nernst also said that, as we know, for any given reaction, that is A mole of A react with B mole of B to give C mole of C plus D mole of D, at any time, if we took the ratio of concentration of product raised to their stoichiometric coefficient divided by concentration of reactant raised to their stoichiometric coefficient, this ratio is known as reaction quotient, that is determined by QC at any time. But if the reaction is going into backward direction also, that means reaction is reversible, then at equilibrium time, when equilibrium is attained, we say the ratio of equilibrium concentration of product raised to their stoichiometric coefficient divided by equilibrium concentration of reactant raised to their stoichiometric coefficient is basically known as your KC. That means equilibrium constant. This is defining us our equilibrium constant. So the key difference between them is that whether the reaction is unidirectional or bidirectional, going forward and backward at the same time, at any given time other than equilibrium, if I take this ratio, then this ratio is known as your QC. Whereas if I take the ratio at equilibrium time, when the concentration is at equilibrium, when the reaction is at equilibrium, the same ratio is known as KC. Value will not be same because it is a time based system. Initially when reaction generally start, we know reactant concentration are always high, product concentration are always less, and equilibrium is established when rate of forward reaction become equal to rate of backward reaction. This is the condition for equilibrium to establish. So this rate will take time to get equal. Till that time, whenever we start the reaction, we have started the reaction T equal to 0 till T equal to T equilibria. In between this time, I take the ratio of concentration of product raised to their stoichiometric coefficient divided by concentration of reactant raised to their stoichiometric coefficient. This will give me a value of QC. At the time of equilibria, at this particular time, if I take the ratio, this will give me a value of Kc. This will give me a value of Kc. Another important aspect for the particular system is that then at equilibria there is another thing, that is delta G of reaction becomes 0. What is delta G? Basically it is very much different than that of delta G node. Delta G is basically the motive force of a reaction. What is the motive behind a reactant to react and give product? If products are generally more stable, then there will be a release of energy. But if products start to combine again and start giving reactant backwardly, and when we say these two motives are equal, at that point of time amount of energy released while forming a product will be equal to amount of energy released when products start reacting and giving reactant back. So at this particular time we will say both G's are same in forward direction and backward direction, and we will not say that overall delta G becomes 0. This is at equilibria, right? So at equilibria my Qc is replaced by Kc, and at equilibria our delta G becomes 0. This much we know from equilibrium. So knowing all this thermodynamic system and this particular equilibrium system, Nernst said, what Nernst said? Nernst gave its equation. Nernst utilized this data and gave an equation for both cell reaction as well as half cell reaction. For both cell reaction as well as half cell reaction. An equation which is valid for half cell reaction and complete cell reaction Initially it was given for half cell, then later applied on complete cell reactions. So Nernst said that in electrochemistry most of the processes are reduction processes. Reduction is generally more favored, as chemical potential is generally less than our electric potential, or we can say electrochemical potential is basically the chemical potential and electric potential of a system. Phi is generally negative for most of the metals, so generally we say that metals generally are more prone to show oxidation, and general reaction that we study in electrochemistry are more of reduction reaction. So it defined the equation for reduction reaction initially, and it says that in a reduction reaction, an species in higher oxidation number gain an electron or multiple electron to get converted into its lesser oxidation state, or I can say an oxidized form gain electron to get into reduced form. This is a general reduction reaction. So if this is a general reduction reaction, I can apply thermodynamics relation on it, and I can say that delta G of this reaction will be equal to delta G node plus RT ln QC. I can simply write this equation over here. Now what is the QC for this particular system? For this particular system, QC is basically concentration of reactant divided by concentration of product. Means reduced form, concentration of reduced form divided by concentration of oxidized form. Concentration of oxidized form. Oxidized form. We can easily write it down, right? QC we can easily write it down. We also know that delta G is basically equal to NF E cell, where E is our known standard potential, and if we are talking about half cell, then we will say delta G of half cell reaction will be equal to minus NF E half cell, which will be a reduction potential, because we are discussing here reduction reactions. Do remember, this is very, very important, which potential we take over here. Similarly, we also know till now that delta G node is equal to minus NF E node, right? Again, this is for half cell, and if this is a reduction reaction, this potential is definitely going to be a reduction potential. In electrochemistry, we took that potential whichever our reaction suggests. If the reaction is reduction reaction, we will take reduction potential. So I will utilize this data over here, I will utilize it, and then I will utilize it and put these values in my thermodynamic relation. So from here I can easily say that negative of NFE, non-standard potential of the half cell, will be equal to negative of NFE node, standard potential of the half cell, plus RT ln ln R by O. ln R by O. Clear? No issue in this. And when I eliminate this negative sign, if I take negative common on the right side, I will have negative of NFE will be equal to negative bracket NFE node minus RT ln R by O. There is no difference in this, right? There is no difference in this. I have just taken minus common. Minus se minus cancel. Then we will have NFE will be equal to NFE node minus RT ln R by O. ln R by O. How can we remember it? This is not a big thing. This is not a rocket science. We can easily remember that NFE is equal to NFE node negative. Whenever you see a negative sign, you will say product concentration will be above in log and reactant concentration will be beneath it. And reactant concentration will be beneath it. Now do remember this. I can again solve it a little bit more from here. What I can do is I can divide this equation on both sides by NF. Divide the equation on both sides by NF. When I divide the equation on both sides by NF, I will simply have E is equal to E node minus RT over NF ln concentration of reduced form by concentration of oxidized form. By concentration of oxidized form. Do remember, whenever there is a negative sign in between, on right side, in ln there will be reduced form concentration higher and oxidized form concentration lower. Or you can simply remember it by always take the concentration of product divided by reactant and put a negative sign before RT by NF. Means this equation also implies that non-standard EMF will be dependent on standard EMF minus RT over NF ln concentration of R by O. Now do remember, R is a gas constant, N is fixed for a particular cell, F is fixed for always, as this is Faraday's constant. We can easily know the value of Faraday constant to be 96500, and this is dependent on temperature as well as concentration of reactant and product. So this is dependent on what factor? This is dependent on temperature and concentration. This concentration and temperature value will define me whether my non-standard EMF at some other concentration, if I have taken the concentration of electrolyte to be 0.1 on one side, 0.01 on another side, and I have taken the temperature of cell to be 35 degrees Celsius instead of 25 degrees Celsius, there will be different values of T, there will be different values of concentration of R and O, and this concentration and T value will tell me whether my new EMF, which is a non-standard now, I have changed the state, so non-standard EMF will be lesser than or greater than my standard cell EMF depending on the concentration values and temperature values. If there is a gas, we will also include pressure in it. If there is a gas, we will also include pressure terms in it. So this is my basically Nernst equation. Another way of writing this Nernst equation is, now do write it down. This is very, very important. This is highly important. If we have an oxidized form and it gains some electron and get converted into reduced form, so for that I have just now derived the Nernst equation, and Nernst equation came out to be E equal to E node minus RT over NF ln concentration of product by concentration of reactant, that means reduced form by concentration of oxidized form. I can also write it as, by using property of log, you know that negative log of m by n is basically log of n by m. We can use this property and I can write the new equation also, or I can say alternate equation, which is basically the same. This equation will be equal to E node plus RT over NF ln concentration of O by R. Concentration of O by R. So I can also write it down in this manner. These are same equation. These two are same equation. Just I have used this property of logarithm. Nothing I have done otherwise. Did you guys get this? Did you guys get the derivation of Nernst equation? How we have derived this Nernst equation? And what does it tell? It tells us the dependency of EMF of a cell on concentration and temperature, as well as pressure and temperature. Is it clear to all of you? If it is clear to all of you, then please type yes in the chat. And if somebody is new over here, they can consider subscribing our channel. If you like the video, please do consider like this video, as well as share it with your friends. So this is our Nernst equation. Now this is very, very important. Directly this formula have came in CSIR exam in 4 marks. In CSIR exam they have asked you in 4 marks this same formula they have asked. The question was change in EMF of a cell is well predicted by which of the following equation? The change in EMF is basically from standard state to non-standard state. What examiner asked you was basically E minus E node. What change have come in EMF if concentration and temperature has changed? So we can easily write it down that change in EMF on going from standard state to non-standard state will be equal to negative of RT by NF ln R by O, or I can also write it down equal to RT by NF ln O by R. This was the option given to you. This was one of the option. You have to select it. Just one option away. Your 4 marks was just one option away from you. This was the question asked in CSIR. This was earlier asked in GATE also in little bit different manner. They just changed the statement of the question a bit. We will discuss main group also. That will be continued very soon. Don't worry about it, Ashu. That will be discussed very soon. First we will try to complete this electrochemistry, and then we will go for main group. Or that may also start in between. Don't bother about it. That may also start in between. No issues regarding that also, right? So this is what our Nernst equation is. That is how our Nernst equation looks like, right? Here from Nernst equation you can also have question based on graphs. You can also see question based on graph from Nernst equation. What kind of question do come in examination? This year also in November 2020 there was a question related to the graph of Nernst equation. Simple question that was not difficult, and it also came in 4 marks. So whenever your examiner set a question from here, either they ask the change in EMF from standard to non-standard state, or they ask you some graphical question. Those question will always carries 4 marks for you. So this is an easy topic to get easy 4 marks in CSIR. Very easily you will get 4 marks in CSIR. So what if somebody say that plot a graph between E cell, or you can say E half cell, and your log of concentration of R by O, or you can say concentration of O by R to be precise. Concentration of O by R, oxidized form by reduced form. R by O they may also give. So I will tell you the method, then you will be able to solve all the graphs by yourself. There will be no difficulties in it. What is the equation? To plot a graph, whatever graph they are asking, take one of the quantity on y-axis and another quantity on x-axis. Initial work is to do this, and then you have to find a relationship between them. then match it with different graphical equation. Either it will be a straight line equation or a parabolic curve or a hyperbolic curve, depending on which equation they are relating with each other. So if I have to do this simple thing, I have my equation which is E is equal to E node. Now this is log, they are asking about log, so I have to convert ln into logarithm. So I will simply multiply by 2.303 RT by NF log of concentration of R by O. Is there any issue in it? No, I think there should not be any issue in it, right? And if I change the sign from negative to positive, basically I want to have a simple this particular expression log of O by R on my x-axis. So to make log of O by R, I will take this log negative in log and this will be replaced by plus. So I can simply write the equation will be E is equal to E node plus 2.303 RT over NF log of O by R, log of O by R. If this is on y-axis, this particular quantity is on y-axis and this particular quantity is on x-axis, this equation resembles to straight line equation. What is a straight line equation? Straight line equation is basically y is equal to mx plus c. Whatever is multiplied to x, here x is log of O by R, that is termed as m, and m is basically our slope, or you can say tangent theta. This is our m, and m is basically slope, and slope of the curve is also known as tan theta, is also known as tan theta. So here slope is 2.303 RT by NF, RT by NF. In December 2020, in November 2020, they said plot a curve between E and T log of O by R. So you can also take this T on x-axis, T along with log of O by R on x-axis. Then your slope will be 2.303 R by NF. That will be the only difference, nothing much, right? So they also asked you this question. They asked you this question in this particular year's examination, 2020, November 2020 examination. So this is our M, right? This is our slope. And what is this C tell us about? This C is basically intercept. This C is basically intercept of the curve. Here the intercept is E node. This is our intercept. This is our intercept for the curve, right? So we can easily plot this curve now. On x-axis I will take E cell. On x-axis I will take E cell or E half cell to be precise. On y-axis I will take log of O by R, log of O by R, and I will have a straight line curve which will intercept the y-axis at a value equal to E node, at a value equal to E node, and the slope of this line will be equal to this slope, that is basically tan theta. This tan theta will be equal to 2.303 RT by NF. So they can ask you graphical question also, this type of graphical question from here. They can simply ask you such questions. Now one more important thing to note down before going further and studying different things. In chemical equilibria and in general, you guys must know that few constraints are always applied. First and foremost constraint is that concentration of pure solid and pure liquid are generally constant. These are constant. Why these are constant? Because concentration is nothing but basically N by V, number of mole by volume, and volume for liquid and solid are generally are always constant. We know this thing. And if this volume is constant, then change is N will not change concentration very much. So we can say that this concentration value will not change highly, or we can say observably, that there will be no such change in concentration because volume is constant and N value is generally very small, 1 mole, 2 mole. So if this is the case, then we will say concentration will generally be constant, and if it is almost constant, so we take a constraint that concentration of any pure solid or any pure liquid are always taken to be constant. And whenever we multiply two constant, for example, if I have an equilibrium constant and I multiply it by concentration of pure solid or pure liquid concentration, this will give me a new constant. This will give me a new constant. Two constant multiplied with each other will give me a new constant. So have a look at QC. QC is also what? Reaction quotient, means it is also a constant. It is also a constant. And if in reaction we have some product and we have some reactant, let me consider that reactant is pure solid. This is pure solid or pure liquid Its concentration will be constant. Definitely its concentration will be constant, and this constant concentration when multiplied by another constant will give me a new constant. Let us denote it by QC dash. That will be equal to only the concentration of products. So what we do in electrochemistry, that in spite of doing whole of this backstory, always what we generally do, that we generally consider the concentration of pure solid and pure liquid to be equal to unity. This, if I consider this to be equal to unity, my new constant equation will be exactly the same which I just derived. So I can say that here, because this concentration are constant, actually they are constant, they are not unity, but what we do is we consider their concentration to be equal to unity. We consider their concentration to be equal to unity. In electrochemistry, what we generally do is that we generally consider their concentration to be equal to unity. For example, if an equation is given to you where a metal ion having unipositive charge gain an electron and get converted into metal zero oxidation state. So we know that iron are mostly stable in aqueous state and metal in zero oxidation state are generally solid. So here what I will say is that concentration of metal which is solid is going to be taken to equal to unity. Actually it is constant, but what we do is we take it equal to unity, because we basically multiplied by QC prior to take it equal to unity, right? So prior we do that, and we here generally take it equal to be unity. So if this is unity, my Nernst equation for the given half cell reaction will be equal to E is equal to E naught minus 2.303 RT over NF log of concentration of product. Now this product is pure solid, only made up of one type of atoms. So I will consider its concentration to be unity and divided by concentration of reactant. Reactant is basically metal in +1 oxidation state. So I will have this equation, right? I can also alternatively write this equation as E is equal to E naught minus 2.303 RT over NF log of 1 by concentration of M positive, or you can also write it as E is equal to E naught plus 2.303 RT by NF log of concentration of M positive. Now do remember, always whenever there is a pure solid made up of single type of atoms or single type of group, whenever there is a pure liquid made up of single type of atom or single type of group of atoms, like water is always having 2 hydrogen 1 oxygen combined, and that is a simple only pure liquid, one type of liquid, that is not a solution. We will always take their concentration equal to unity in electrochemistry. Basically these are not unity, these are constant. Sometime examiner may ask you, for particularly in JAM examination or DU BHU M.Sc entrance examination, are these concentration equal to 1? No, they are equal to constant. They have some concentration, like pure water generally have a concentration of 55.55 molar concentration, and we generally, it is always constant, so we generally take it equal to unity. We basically multiply it by QC or KC, and then new constant is defined. That new constant always will have this factor multiplied to it, so we take the concentration equal to unity. We consider it, we do not mean that it is actually equal to 1. It is always considered. Do remember this also. It is very, very, very important point to note down. Highly important to note down. Please do note it down, right? Now from here also, from this one also, they can say that temperature, if temperature is 25 degrees Celsius, if temperature is 25 degrees Celsius, but concentration is not equal to 1, but concentration is not equal to 1 molar, then also we say this is not a standard state. Any one condition change, any one condition, the either concentration condition or pressure condition or temperature condition, any one condition deviates from the standard state, that means it is not a standard state anymore. For a state to be non-standard, it does not mean that only one thing should be changed. Anyone can be changed. If all are changed, then also it is a non-standard. If temperature, pressure, concentration all are changed, it is a non-standard state. Only one of them is changed, it is again a non-standard state. Do remember it. At 25 degrees Celsius, if they have given you 25 degrees Celsius temperature, so at 25 degrees Celsius, or I can write it as 298 Kelvin, we have 2.303 multiplied by R, that is basically 8.314 multiplied by 298 Kelvin divided by F, which is 96500. Here electron count is 1, so we can simply write that N value is basically 1 over here. So this whole equation, this whole multiplication and division, if I solve, this comes out to be equal to 0.0591, which is approximately equal to 0.06. So at 25 degrees Celsius, you can write the equation as E is equal to E node plus 0.0591 divided by N. Here N value is 1. You can also write 1, no issues. Log of concentration of M positive. Log of concentration of M positive. This 0.0591 value will only be there if the temperature is fixed at 25 degrees Celsius. If some other temperature is given, then we have to use this whole equation and find out the exact value of 2.303 R into T by F. Right. So they can also ask you graphical question from here, that plot a graph between E cell and log of concentration of Mn positive. Plot a graph between E cell and log of concentration of Mn positive. Now you can easily plot it, no issues. Now you can easily plot this graph, there is no issue in it. You know the equation very well. This equation comes out to be E is equal to E node minus 2.303 plus RT over NF log of concentration of M positive, right? We know this equation. And if I put this equal to Y, if I take this quantity on x-axis, this will be my M and this is going to be my C. This again looks similar to straight line equation. That means if we have on y-axis E cell and on x-axis if we have log of concentration of M positive, then we can find it to be a straight line graph with a positive slope, increasing slope, where slope value, M value, or you can say tan theta value will be equal to 2.303 RT by NF, and this line will cut my Y graph, Y axis at a value equal to E node. At a value equal to E node. You can again plot it. There is no issue in it. You can again plot this one. There will be no issue in it. Right. So these are basic of Nernst equation. Now this equation means a lot. When my E cell will be greater than 0 or greater than E node, less than E node or equal to E node, this means a lot of things. So for that to know, for that we will consider few things. We will study some cases. Let us study first case. The first case is, I can simply say, if my concentration of M positive ion is equal to 1 molar, then log of 1 is basically equal to 0. Log of 1 is basically equal to 0. And if this log 1 is 0, if this term is 0, x is 0, x multiplied by any m, that will also be 0. And at this particular time, I will say that E cell non-standard EMF will be equal to standard EMF for my this particular reaction which we are discussing over here. Do remember, this concentration can be greater than 1 or less than 1. There can be these two cases also. In case 2, I will consider if concentration of M positive ion is greater than 1 molar. Any concentration you can imagine. Let me consider that if this is 10 molar concentration, if this is 10 molar concentration, then log of 10 is basically equal to 1. Whenever we put in log value greater than 1, it will always give us a positive value. It will always give us a positive value. Log of 10 equals to 1, right? So I can say whenever we put greater than 1 value in log, 1.1, 1.2, 2, 3, 4, any value, we have log of M positive, that will give us a positive value. That will give us a positive value. So if this particular system give us a positive value, then we can say that X multiplied by M. X is positive, M is always positive. This whole thing will be positive. Means we will have E equal to E node plus some positive value. Plus some positive value. Means if E node is 5, then we will have some value in addition to it. Either it will be 0.1, 0.2, 0.3 or 1, 2, 3, any value, and that whole sum will give us a new value for our non-standard EMF, and this new value will always be greater than E node. So I can simply sum it up and write it down as, here whenever concentration of Mn positive will be greater than 1 molar, log will give me a positive value, and for this particular system E non-standard will be greater than E node. E non-standard will be greater than E node. In case 3, we can have third case also. We can have third case also where the concentration of M positive ion can be less than 1 molar. And whenever we put a value lesser than 1 molar in log, lesser than 1 in log, for example 0.9, 0.8, 0.7, 0.01, any value which is less than 1, then log generates a negative value. And if this value is negative, X is negative, so I can say X into M will be negative, or I can say from my equation E will be equal to E node plus some negative value. That means if E node is 5 and I subtract any particular value from it, 0.1, 0.2, 0.3, or I subtract 1 from it, I will have a new value which will be always lesser than 5. So I can simply say that at this particular situation, we will have new E non-standard EMF of the cell lesser than standard cell EMF. That is what we generally mean by these statements. That is what we generally interpret from. That is what we generally interpret from Nernst equation. That is what we generally interpret from Nernst equation. Means, do have a look at it. Do have a look at it. Whenever this log Mn positive, log of M positive, this value is 0, my E is basically equal to E node. My E is basically equal to E node. Whenever this value becomes more and more positive, log of M become more and more positive, my E value will always be higher than E node. Will always be higher than E node, because E node is just fixed at a particular value, right? This is E node. My E value will always be higher than E node. And if I extrapolate this graph on this negative x-axis, I can always say if my log of M positive is having a negative value, then my E cell will always be less than E node. Will always be less than E node. That is what we can interpret from this graph. That is why these graphical studies are more and more important. So this is the basic introduction of Nernst. We have applied it on half cell. In next lecture, we will find Nernst equation for complete cell, how we can apply the Nernst for complete cell reaction, and then we will move on to the application of Nernst equation, where we will find derivation of thermodynamic data, equilibrium constant, stability constant, formation constant, activity coefficient. These all application we will discuss in upcoming lectures. So if you are new to the channel, please do consider subscribing our channel. If you like the video and the content of the channel, please give us a like, and whenever you subscribe the channel, please press the bell icon also for the regular updates. Do share it with your friends whenever we are live. Please share it with your friends either on WhatsApp or on Instagram or on Facebook or on Telegram, wherever you have joined. You can share these sessions so that more number of people come to our live stream. More people come, more question will be discussed. Just like in previous lecture, somebody asked a question and that clarify concept of many others. So healthy discussion will take place, and if healthy discussion take place, then everyone will gain out of it, right? So what you have to do is nothing much. If you like the content, share it with your friend. If you like the content, like the video. If you are new to the channel, please subscribe the channel. So by those words, I will be ending this lecture over here. In next lecture, I will be discussing with you guys Nernst equation, how we derive Nernst equation for complete cell, and then we will discuss the first application of Nernst also in the next lecture. So thank you very much for joining. We'll see you very soon with another lecture of electrochemistry. And if you want to read this electrochemistry in Hindi, there is already, we have covered it in Hindi by our two marathon classes. In a playlist you will have marathon videos, and there you can find 2 marathon classes for electrochemistry where theory and questions have been discussed already. So if you want to study this in Hindi, you can go and watch those 2 videos anytime you want. They will be available there for all rest of the time also. Thank you very much.